Welcome to Audio ML Papers, roundup for October to mid-November.
And welcome back. This is where we distill the cutting edge of audio ML research, helping you quickly grasp the technical innovations, the practical applications, and really the long-term impact of the latest preprints and conference papers.
Yeah, the ones that are really defining what's next.
Mhm.
This is your shortcut to understanding the major shifts happening right now in the field.
Absolute.
Okay, so let's unpack this week. This week's selection, it signals a really clear and, I think, a vital shift in audio AI research. For a long time, the community was, maybe rewarding systems that got great scores on clean, controlled lab data sets.
Perfect acoustics, scripted lines.
Exactly. Constrained emotions. But that era feels like it's really ending. We're moving aggressively toward a focus on naturalistic, expressive, and truly human-centered performance.
It's the sound of the future demanding real-world performance, not just lab perfection. I mean, if an AI can't capture that spontaneous hesitation or the way people talk over each other or the subtle shift in tone that tells you everything, it just fails when you deploy it.
Right.
And this trend, it forces us to wrestle with the hardest issues in the field. How do we actually evaluate human-aligned quality? How do we scale our data without losing all that natural richness? And how do we build efficient models that can handle all this new, messy complexity?
That transition from, pristine lab data to messy reality.
Yep.
That's the theme. And the papers we have this week, they reflect that transition perfectly. We have 3 really powerful papers covering those key areas.
A great lineup.
Yeah. First up, we're looking at evaluation standards. There's a highly sophisticated framework from Carnegie Mellon University, CMU, for evaluating AI role-playing. Then we pivot to data, looking at a massive, spontaneous emotional podcast data set from Johns Hopkins. And finally, we dive into architecture, specifically efficiency, with the state-of-the-art video-to-audio generation model from KAIST that was just presented at NeuralPS 2025. So it's the whole stack, really. Data, metrics, and models.
The perfect snapshot. Let's get into it.
So kicking us off in the evaluation space is a paper that tackles a problem that has been, I think, just persistently plaguing conversational AI.
Yeah.
How do you objectively measure performance when an AI is supposed to adopt a specific persona or a role?
It's such a hard problem.
The paper is Speech-DRAME, a framework for human-aligned benchmarks in speech role-play. It's authored by Jiatong Shi and colleagues from Carnegie Mellon University. It was published on the Arxiv, that's Arxiv, on November 3rd, 2025, and landed with a huge impact score of 93, so the community is already paying close attention.
And they should be. The problem they identify here is just fundamental. It's highly relevant to anyone building, complex conversational agents. Think customer service, entertainment, education. Right now, the methods we use to evaluate an AI that's supposed to be, say, a doctor or a financial advisor, they're just too crude to be useful.
And what defines that crudeness? What's the main issue?
The primary issue is our reliance on unspecialized metrics, or even worse, unspecialized model judges. The authors note that a lot of pipelines just use, and I'm quoting here, audio large language models as zero-shot judges.
Okay, so you're just asking a generic model, hey, how good was that performance?
Exactly. As if it inherently understands the nuance of human role play. And these models, they fail spectacularly because they miss all the crucial paralinguistic cues, the specific intonation, the rhythm, the emotional texture, the pace that actually defines a role.
Plus, those judges tend to just collapse everything, fidelity, how well it stuck to the role, the emotional tone, into a single coarse score that ends up being pretty meaningless.
That's it. It's a lack of granularity. If you're a developer and your model gets a low score, you have no idea which part of the performance is failing. Without a targeted metric, your iteration just stalls.
And CMU's involvement here, that instantly lends credibility. I mean, Carnegie Mellon has this undeniable decades-long reputation in speech research. Foundational. Yeah, from early synthesis all the way to modern LLMs. So when they publish a paper focused on defining evaluation standards, especially one about human perception, the field is going to pay immediate attention. They're pushing us past just simple fidelity.
Right. They're asking, can the AI truly act? Can it adhere to our contextual human expectations? The technical challenge they frame is actually deceptively simple.
Which is?
How do you objectively measure if an AI is acting like a firefighter versus, say, a librarian? In the real world, these roles aren't just about vocabulary. They're defined by these subtle, learned, paralinguistic stereotypes.
A firefighter needs to sound calm, measured, authoritative.
Exactly. While a librarian might need a quiet, thoughtful tone, And measuring how well a model adheres to these subtle social expectations, that's the whole goal.
Okay, and this is where it gets really interesting, because the core innovation of Speech-DRAME is their dual evaluation strategy. They move past that single score by splitting the assessment into two critical dimensions.
And that dual approach is the big breakthrough here for evaluation. The first dimension is what they call archetype evaluation. This is a top-down assessment.
So it's measuring adherence to the stereotype.
The broad, high-level role stereotype, yes. The evaluation model has to understand the universal, often culturally reinforced vocal traits of a generic firefighter or teacher. It's answering the question, does this voice fit the broad social expectation of the role?
And then you have the counterpoint, which anchors the whole thing in reality. Realism evaluation.
Precisely. Realism evaluation is the bottom-up approach. It's grounded in actual unscripted human speech examples. It captures nuanced real-world delivery independent of the stereotype.
Okay, so give me an example.
Think of it this way. The archetype score measures if the AI sounds like the idea of firefighter. The realism score measures if the AI just sounds like a complex human being having a conversation with all the subtle emotional shifts and natural imperfections.
Right. The latter is critical for, say, a therapeutic bot where authenticity is everything.
You got it. And to implement this, they didn't just propose a theory. They built a complete ML pipeline with 3 integrated components.
Can you walk us through those?
Sure. So first, you need the foundation, the Speech-DRAME Evil Bench. This isn't just audio. It's a meticulously curated data set with bilingual human annotations, all designed to capture those 2 dimensions, archetype and realism, across a bunch of different roles. That's your ground truth.
And that feeds into the engine itself.
Yep. The engine is the core model, DRAME Evil. This is the fine-tuned evaluation model engineered specifically to predict those human scores accurately. They aren't just using some off-the-shelf audio LLM here. They're optimizing a model to act as a sophisticated surrogate for the human ear.
And the third part.
That's the Speech-DRAME Roll Bench. It's a standardized test set. It means any new synthesis model that comes out can just be slotted into this roll bench for a fair comparison against all the previous methods using this new high-fidelity metric. It standardizes the whole process.
So the magic is really in that fine-tuning of DRAME all.
That's where it all comes together.
Okay.
They're optimizing a loss function that correlates features not just with acoustics, but with the subjective human judgments from the Evil Bench. That ensures the final metric is genuinely useful.
And the numbers they reported really speak volumes about its success. They achieved significantly stronger agreement with human ratings compared to those zero-shot judges we talked about. They improved the Pearson correlation, which is a standard measure of how well the model score and human score line, up from 0.480 to 0.629 for the archetype dimension. For realism, is even more dramatic, from 0.390 all the way to 0.625.
Let's pause on that Pearson jump for a second, because for any practitioner listening, this is huge. Pearson values go from -1 to +1. Jumping from the 0.3 to 0.4 range, which is, weak to moderate correlation, up to the low 0.6 range is transformative.
And why is that so transformative in this specific context?
Because human evaluation is inherently noisy. Even 2 human judges won't agree perfectly on something this subjective. The fact that the DRAME Evil model correlates with human judgment at a level of 0.625, that means the model is probably correlating with the ground truth better than 2 humans often correlate with each other.
Wow. Okay.
It makes the system a genuinely useful, high-fidelity, and frankly cost-saving surrogate for expensive human evaluation panels. If you're running hundreds of experiments, that is indispensable.
That strong correlation is the green light for adoption. This has immediate applications for any conversational AI, especially voice assistants that need to change personas.
Right.
Switching from a formal news anchor voice to a casual one.
It's a clear path toward truly human-aligned AI performance, but it does raise an important question, and it's a limitation they acknowledge themselves.
The classic annotation bottleneck.
Exactly. While it's powerful, the framework still relies heavily on that initial set of high-quality human annotations for the Evil Bench. If you want to expand to dozens of new, culturally specific roles or languages, you're back to gathering and annotating human data, which limits scalability.
And you have to be skeptical about generalizability. What makes a voice authoritative or polite can shift dramatically across cultures and languages.
That's the tension. Can we use the high-fidelity insight from Joy-Mevel to bootstrap models that don't require explicit human annotation for every single new role? That's the obvious next step for research.
All right, shifting gears from the challenge of evaluation to the challenge of data. We're landing on a paper that tackles a huge constraint in audio ML, getting quality data that reflects real, messy, human emotional life.
Yeah, this is a big one. The core problem has always been that our expressive synthesis and voice conversion models relied almost entirely on acted studio-quality emotional speech data sets.
Like IMUCAP.
Exactly. Recorded in clean rooms with actors reading from a script, they just fail to capture the richness of real-life spontaneous communication, where emotion is often subtle, mixed, or unintentional. I mean, studio-acted empathy just sounds hollow compared to the real thing.
And Johns Hopkins University, with its serious credibility in speech processing, tackled this data bottleneck head-on. Their team, led by Zongying Du, published NaturalVoices, a large-scale, spontaneous, and emotional podcast dataset for voice conversion on October 31st, 2025. This one also scored a high 92 on the impact scale.
And their response wasn't just to collect more data, which is often the first instinct, but to collect richer data. NaturalVoices is a massive 5,049 hours of spontaneous podcast recordings. The scale is transformative, yes, but the context unscripted natural conversation is what really changes the game.
So it incorporates all that messy stuff that Speech-DRAME is trying to evaluate. Overlaps, hesitations, different mics.
All of it. And processing over 5,000 hours of unscripted, often noisy audio is a monumental technical undertaking. This wasn't just a simple web scrape. The pipeline they detail is fascinating from an engineering perspective.
It sounds like an industrial-scale ML project.
It really is. They had to ensure the data was actually useful, so they built this sophisticated processing chain. It starts with automatic speech recognition for transcription, then speaker diarization identifying who spoke when, which is crucial in podcasts.
Okay, let's zoom in on diarization for a second. That's a major challenge in the wild, right? Especially with overlapping speakers.
It is. It requires sophisticated clustering and boundary detection. Unlike a clean environment, real conversation has rapid turn-taking and frequent overlaps. If you label the wrong speaker or misattribute an emotional line, your voice conversion model will learn faulty connections. The fact that JHU built a pipeline robust enough to handle this is a huge engineering achievement.
So what comes after diarization?
Speech quality assessment to filter out the unusable parts, and then sound event detection to flag things like music beds or background noises that researchers might want to exclude.
But what really sets this data set apart, and ties back to our last paper, is the sophistication of the emotional annotation.
Yes, this is the really fascinating part. They wisely chose not to just use categorical labels like anger or happiness, which is too simple. Instead, they included continuous attributes from a well-known psychological model: arousal, valence, and dominance.
Can you quickly define the arousal, valence, dominance, or AVD scale for listeners who might not be familiar with it, and why it's so critical here?
Absolutely. Think of emotion not as a distinct bucket, but as a point in a 3D space. Valence is the pleasantness, positive versus negative. Arousal is the intensity, calm versus excited. And dominance is the level of control, so submissive versus in charge.
And this allows for an incredible degree of nuance.
Exactly. Instead of training a model to sound happy, which could be anything from delighted shrieking to quiet contentment, you can train it to sound low arousal, high valence, medium dominance, which perfectly maps to quiet contentment. This level of control is invaluable for fine-tuning a voice to match the subtext of a conversation.
So if you're building, say, a character in a game that needs to show subtle disappointment without sounding fully angry, the AVD annotations are the only way to get that fine control.
It allows the model to learn the degree of an emotion, not just the category. Now let's look at the practical results. Their experiments clearly show that models trained on NaturalVoices do produce more expressive, natural-sounding speech. It validates their whole hypothesis.
But if we connect this back to the bigger picture, and we look at their Table 6 results specifically, there's still a performance gap that's pretty telling. It shows the limits of our current architectures.
Right. Table 6 compares models trained on NaturalVoices and then tested on both synthetic audio and real, unseen, spontaneous recordings. The metrics, especially for naturalness and speaker similarity, they show a substantial drop-off when the models hit that truly in the wild speech.
So it suggests that while NaturalVoices provides the right kind of data, our current ML architectures, even the state-of-the-art ones, can't fully master that naturalistic expressiveness yet. We have the data, but the algorithms can't fully exploit it.
The complexity of modeling spontaneous emotion, the timing, the pitch shifts, it's still ahead of our current generation of models. They get the core mood, but they struggle with that perfect, seamless replication that really fools the human ear.
So for the practitioner, the applications are huge, better dubbing, more expressive voice assistants. But you have to consider the practical constraints. Training on 5,000 hours of this messy data is computationally immense.
And that leads to the crucial quality trade-off. The variations in podcast audio background music, different mics, room acoustics, while they're great for robustness, they might actually hinder performance for applications that need clinical consistency.
Like medical transcription or voice biometrics.
Exactly. NaturalVoices is excellent for expressiveness, but it might be too messy for applications demanding absolute pristine quality. It just highlights how specialized our data needs are becoming.
So we have this massive, rich data set that pushes the boundaries of expression, but also exposes the shortcomings of our existing models. A really powerful conclusion.
And that attention algorithms struggling to meet the challenge of rich data brings us perfectly to our third paper, which is all about architectural ingenuity and efficiency. If you can't just endlessly scale data or models, you have to get smarter about how you train them.
Okay, our final paper is from the Korea Advanced Institute of Science and Technology, or KAIST, and it was presented at the prestigious NeurIPS 2025 conference. So high-profile venue, strong engineering school. The paper is titled Model-Guided Dual-Role Alignment for High-Fidelity, Open-Domain Video-to-Audio Generation.
This one addresses the really challenging problem of generating realistic, synchronized audio from silent video. Generating a sound that perfectly matches a footstep, a door opening. It's difficult. It requires deep cross-modal understanding.
And previous models often relied on these complex external guidance mechanisms.
They did, and those mechanisms, while they work, add a lot of computational cost and complexity, especially at inference time. KAIST's reputation signals that they found a smarter, more integrated way for the model to guide itself.
So what's the breakthrough?
The core breakthrough is replacing the standard classifier-free guidance, or CFG, which is a really common technique in diffusion and audio models, with what they call model-guided dual-role alignment. Let's break that down.
Yeah, start with CFG. Why is it inefficient?
CFG typically works by running two separate forward passes of the model during sampling. One conditioned on your prompt, in this case the video, and one that's unconditioned. The difference between those two outputs is used to steer the generation toward higher quality.
And that's expensive because you're basically doubling your inference time.
Exactly. So MG Audio says, we don't need two passes if we just bake the alignment mechanism directly into the model's structure during training. It internalizes the guidance.
Okay, so it has this elegant three-component system. Let's start with the architecture.
They use a scalable flow-based transformer architecture. This is really important for efficiency. Flow-based models are different from autoregressive models or standard diffusion models. They allow for highly parallelized inference, which is much faster.
And then the second part is the innovative dual-role alignment mechanism.
Yes. The audiovisual encoder acts simultaneously as the standard conditioning mechanism, telling the model what to generate, and as the source for feature alignment. It's serving both semantic and guidance purposes at the same time.
Which brings us to the third piece. Their novel model-guided objective. They're essentially embedding the alignment process into the loss function.
Right. It forces the generated audio and the input video features to co-evolve for perfect synchronization. The model learns to trust its own internal features for guidance, which removes the need for that external CFG.
And the results. They speak volumes about this strategy. MG Audio achieves state-of-the-art SOTA performance on the VGG sound benchmark. They get a fresh-head audio distance, FAD, of 0.40.
We should probably explain FAD like we did for Pearson R. What is it, and why is 0.40 a SOTA?
Good point. FAD, or fresh-head audio distance, is a key metric for evaluating generated audio quality. It measures the distance between the feature distribution of your generated samples and the real data. Lower is better. Scores for other models often hover above 0.50, so hitting 0.40 is a pretty significant leap in realism for this task.
But here's the kicker, and this is the big one for anyone focused on deployment. It achieves this SOTA performance using only 131 million parameters.
Only 131 million. That's a huge competitive advantage.
It is. I mean, many SOTA multimodal models are swelling into the billions of parameters, demanding huge amounts of compute. A model this small that performs this well opens up possibilities for edge computing, for smaller research teams. It proves that clever architecture can still win out over brute force scaling.
What stands out to me, though, isn't just the small size, it's the data efficiency they highlight.
That's the other side of the coin. The fact that MG Audio maintains competitive performance even when trained on only 10% of the full data set, you can see this in their PIT. Figure 1 demonstrates remarkable data efficiency. For labs where annotating massive data sets is just too expensive, this shows a smarter algorithm can learn critical alignments from way less data.
So the applications here are pretty clear. This could revolutionize video production workflows, maybe improve text-to-video models by adding that synchronized audio layer.
And accessibility tools, too. Automatic realistic audio description for silent videos. But the authors are admirably honest about two limitations that practitioners really need to heed. First, while the model is great at environmental sounds, footsteps, collisions, it still struggles with complex human vocalizations in speech. You probably need to do some speech-specific fine-tuning for that.
Yeah, and the second one.
Inference speed. Despite the efficient architecture, it's still not real-time. The iterative sampling process is a practical bottleneck. It's fast for batch processing footage, but not yet fast enough for, say, a real-time virtual environment. It's a trade-off. High quality, small size, but still some latency.
Okay, so having gone through these three really technical papers, evaluation, data, and efficiency, we can step back and see the bigger themes emerging at the cutting edge of audio ML.
The synergy between them is actually remarkable. Even though they're coming at the problem from completely different angles, they all point in the same direction.
Let's start with theme 1. The move to naturalistic in the wild data. I mean, there's just this pronounced, unavoidable trend toward using naturalistic data.
It's everywhere. Both NaturalVoices, with its messy podcast audio, and Speech-DRAME, with its realism evaluation grounded in actual human speech. They both emphasize moving beyond those pristine lab conditions.
The implication is clear. The field knows that clean, acted data just doesn't translate to robust real-world apps.
Yeah.
We're now consciously embracing acoustic variation as a feature, not a bug.
Exactly. We're sacrificing some of that pristine acoustic quality for behavioral richness and context, the ability to model hesitation, overlap, and spontaneous emotion.
And theme 2 builds right on top of that. Sophistication in evaluation. It's not just about optimizing raw technical metrics like FAD anymore. The metrics themselves have to model human perception.
And this is why the overlap is so tight. Speech-DRAME directly tackles human-aligned evaluation with its archetype and realism scores. You need that dual approach because our models are being asked to handle these complex human-like roles.
At the same time, NaturalVoices provides the rich data foundation with its multidimensional AVD emotion attributes, so we can benchmark models not just on whether they sound happy, but how happy.
Right. And then MG Audio comes in and shows that superior performance and metrics are achieved through smarter training objectives. It proves that innovation in the loss function leads directly to higher quality, human perceivable results. We're chasing human perception now, not just raw numbers.
Which brings us to theme 3. Efficiency versus scale. This is the classic algorithm versus data tension that every practitioner has to deal with.
And it's probably the most interesting tension right now with immediate practical implications.
On one hand, you have MG Audio making this compelling case for algorithmic ingenuity. Its smart alignment lets it achieve SOTA results with just 131 million parameters. It's the triumph of clever engineering.
But on the other hand, you have NaturalVoices providing this massive data scale, over 5,000 hours, yet their own results show that our current architectures can't even fully exploit it yet. It's the data-first approach, only to find the modeling capacity is still lagging.
So the tension is, what should a research team prioritize? Expensive data curation, hoping architectures catch up? Or the MG Audio path, focusing on hyper-efficient algorithms that can work with smaller data sets?
The conclusion is inescapable. You absolutely need both. But in the short term, scaling models isn't the only answer. Smarter algorithms, like MG Audio's, are proving highly effective, especially for teams where compute and annotation budgets are tight. Architectural ingenuity still provides a massive return on investment.
And if we look forward, the next step seems obvious. The thing that's conspicuously absent is a unified framework.
That's the missing piece. Imagine an integrated system. You start with MG Audio's architectural efficiency, you train it on the emotional richness of a data set like NaturalVoices, and then you use the Speech-DRAME framework to precisely evaluate its role-playing against human perception.
That integrated system where architecture, data, and evaluation are all designed for the same goal of human-aligned performance, that would be the next major leap for audio AI.
This week's papers, taken together, they signal a decisive shift toward human-centered audio AI. one that prioritizes naturalness, expressiveness, and real-world applicability over just, technical perfection in a sterile lab.
Yeah. The complexity of human communication, whether it's adopting a professional persona or expressing subtle disappointment, that is now the primary ML objective.
It is.
And for you, the practitioner or researcher planning your next project, the takeaways are highly tactical. The field is moving fast toward applications that require a deep understanding of human nuance. The days of treating speech as just acoustic pattern matching, they're over.
Specifically, if you're building conversational AI, the Speech-DRAME framework should really become your new standard for evaluation. You have to move beyond zero-shot judges and embrace these human-aligned metrics.
And if your voice conversion model sounds robotic, you need to be training on spontaneous data with continuous annotations like AVD, the kind you find in NaturalVoices.
Yeah.
That scale and richness, it's just non-negotiable for true expressiveness.
And finally, MG Audio shows that engineering smarter training objectives like self-guided internal alignment offers a powerful parameter-efficient alternative to just endlessly scaling your models. Efficiency is a form of innovation.
So future research has to focus on integrating all of this. The ultimate goal isn't just an AI that processes speech, but one that truly understands and generates human-like communication in all its messy, emotional, contextual complexity.
We're moving toward AI that understands the gaps between the words, the implied meaning, the hesitation that signifies doubt. What does the first widely adopted AI system that genuinely understands subtext actually sound like? That's the challenge for next year. That's the bar we need to clear to move beyond synthesis and into genuine conversational intelligence.
Thank you for joining us for this roundup of audio ML papers. We'll catch you next time.